All right. We are in module 8, where we'll be learning about interval estimation. And in the last chapter, we discussed how we use the sample mean as a statistic, as this statistical inference for the unknown parameter of the population. And now we'll start to build off this as we branch further into inferential statistics with developing estimates and hypothesis testing. So this is where things start to get interesting when it comes to testing different aspects of statistics and making inferences based off of that. So in this chapter, we'll focus on estimation through inference testing. Specifically, we'll use the confidence interval to approximate a range of values an estimate of the parameter from the population can take. So we'll develop and interpret confidence intervals for the population means in this chapter. And first, we'll just explain, what do we mean when we say a confidence interval? So I want you to think when you order a delivery online and they give you an estimate of when your package might arrive. So they might say between 2 to 3 business days, depending on the shipping policies that they have. We can consider this to be a confidence interval, as it's this estimated range of values that the random variable of X, or the delivery time, where X represents the delivery time, could take. And this tells you as a consumer when you can expect to receive your package. And you might be surprised if you received your package before this time interval or after, and you might call and complain. So this is what we should think about when we say confidence interval.
So a confidence interval is basically when I order a package from Amazon and it says it'll be to me by the 25th, between the 25th or the 27th.
Yeah, exactly. Like if they told you right at the 25th at 12:07, that's more of like a specific estimate, but they give you this range of values so that they are more likely to be right.
Okay, cool.
And yeah, it's kind of similar when we were doing the upper and lower confidence control limits, not confidence levels, in the last chapter, thinking about like, these are the range of values that your production process could take. And if it goes above or below, then something's out of control, something's wrong. So if you got your package before that time and after that time, something's wrong. But we'll definitely dive into more of these details as we progress on. And so kind of hopping off that, so far we've really talked about point estimates when we say this sample mean, but often it's more informative and more accurate where we can provide this range of values as an interval rather than that single point estimate. So for example, saying if your package arrived exactly at 12:07 on Wednesday, it's very unlikely that the company would actually be able to meet these expectations. And so this main ingredient for developing a confidence interval is the sampling distribution of the underlying statistic. So for example, what we just covered in the last class with the sampling distribution of X bar, which was that sample mean, to describe how the sample mean varies between samples. Because recall, this is the variability between samples that we are measuring with the standard error of the X bar. So if this standard error is small, then it implies that the sample means are not only close to one another, they're also close to the unknown population mean. So what if we took a new sample and we want to see how the mean and standard deviation change in the sample distribution would result? So for example, if we had a 95% confidence interval, that means that if we calculated a confidence interval from 100 different samples, about 95 of them would contain the true population mean, and we would only exclude this population mean 5% of the time. And when I say exclude, it means that we guessed that population mean and it wasn't within that confidence interval. So going back to that Amazon package, if we said 95% confidence interval that you'll receive your package between the 25th to the 29th, we could say 5% of the time you might receive it before the 25th and after the 29th. And think of this.
Oh, yeah, sorry.
Yeah. Oh, no worries. What's up?
So it's basically like I'm 95% sure that your package is going to be here on this date. That's the confidence.
That's definitely the way it is more straightforward to interpret, but technically it's more so guessing that the interval will be within this scope, and 5% of the time it will not be within this interval. And we'll get more into how do you interpret it, but kind of intuitively what you said makes sense. But technically what we're doing here is calculating the proportion of instances where we get it right, where the population mean is within the interval.
Got it.
But we'll like hone in on that because it's a little tricky with the interpretation. And the textbook also does a good job of explaining really what it is that we're calculating here. But in kind of in short terms, you can think of it that way. But we'll dive a little deeper into that.
I have a quick question.
Sure.
Another way to think about it, because it just came to my mind. Would it be like an athlete that was practicing their free throw? Like they would say, like out of 100 shots, like 80 of them would be in and like 20 of them would be out. Would that be like a confidence interval?
I think that could be an appropriate metaphor to take, because we're thinking of this margin of error, where that would be the proportion of instances where they didn't, make the shot, where it wouldn't be within that interval. So I think that would be an appropriate metaphor for us to use.
Okay. Yeah, that's it. Okay. Thank you.
Yeah, no worries. I like that. So yeah, kind of hopping off that and just talking through this, we're going to just repeat it a couple times, saying this confidence interval, where if you took the, 100 different samples and saying 95% confidence interval, 95% of those samples would contain the true population mean. And think of this gap of that margin of error of that 5% that is not included, the true population mean within that confidence interval. And this margin of error accounts for the standard error of the estimator. So that is when we get it wrong, essentially. So it's important to stress that this confidence interval depends on the mean of the population to be normally distributed. So we can use the symmetry of the normal distribution to inform this area under the curve. So this is just talking about assumptions we make in order to apply this 95% confidence interval. We assume that the distribution of the random variable X is normally distributed, so we can leverage all of our kind of overly simplified expectations that the tails are symmetric, and we can use this area under the curve to calculate that proportion of probability that we would expect to see. So we can now then slice and dice the margin of error around the confidence interval. So in general, the confidence interval is constructed using a point estimate with this margin of error that either under or over miss that true population parameter that we're trying to approximate. So an analogy, I like the sports one, but another one that I thought of in preparation for class is voting predictions, where in elections, different pollsters create the probability that a candidate will win given the estimates gathered from polls. So here are some plots of confidence intervals from the 2016 election that shows the distribution of outcomes for the national popular vote. So this website always has really great visualizations, 538. And so this was just one screenshot I took from it, where it shows the different outcome, and it actually clarifies what this confidence interval would look like, where 80% chance of the outcome falls within this range. So there's this margin of error that accounts for the variability in how they're gathering samples from all the polls. So they have this ability to say, this is this point estimate where perhaps 48.5% chance that Clinton would win, but you have this distribution to really point out this margin of error and this confidence interval around that point estimate. So this communicates that variability and the standard error of the samples polled. And so the goal of having these confidence intervals with the margin of error is that it enables us to apply our same set of tools we've been learning the last few chapters of using the Z-score in order to calculate the probability from a normal distribution. So next, we will construct a confidence interval for when the mean and standard deviation are known. But any questions regarding this? Okay. So let us go through an example of constructing a 95% confidence interval for mu, the mean, when the sampling distribution of X bar is normally distributed. Again, we have to assume that it's normally distributed in order for us to apply the symmetry of the tails and use our standard z-score table. So using the symmetry, we compute that the remaining area under the curve outside of our 95% confidence interval. So knowing that the area under the curve equals 100% or 1 because of the infinite tails that we're accounting for. If we subtracted 95% from that 100%, it leaves us 5%. And we want to calculate that area under both tails. So we divide that 5% by 2. And then we would just use the z-score table to get that value of the z-score that we would then use for calculating the probability of the tail being 0.025 because we took that 5 and divided it by 2. So recall the way we use the z-table to calculate the probability of seeing a value in the upper and lower tails. So in this case, we get 1.96 just using the table, or you can use Python for getting that value. And this would imply that there is a 0.95 probability that the sample mean of X bar will fall between the mean minus 1.96 times the standard error and the mean plus not 1.96 times the standard error. If the sample size n of how many samples are we taking are drawn repeatedly from a given population, this means that 95% of the computed sample means of X bar will fall within the interval, and the remaining 5% will fall outside of this interval. And this is where I'm going to just clarify with that interpretation that was mentioned. So for instance, the above 95% confidence interval does not imply that the probability that the mean mu falls in the confidence interval is 0.95. So it's not saying like there's a 95% chance that it falls within this interval. It's more so saying that when we take this sample mean that it falls within this interval or does not fall within the interval. We're simply implying that if numerous sample sizes of size n, for example, are drawn from a given population, then 95% of the intervals formed by this formula will contain the real value of mu. So thinking back to the pollster case, this means that if they took 100 samples and calculated the sample mean with a 95% confidence, then 5 times out of the 100, the sample mean would fall outside of the confidence interval, perhaps just due to the variability in the sample itself, or just kind of random chance. So this randomness comes from the sample estimate, not the true mean of the population. Since many of our possible sample means can be derived from a population, our goal is to just be right 95% of the time, thus giving us this 95% confidence. And as we get more into hypothesis testing, these concepts will continue to build off of each other and be very similar. So when we get into hypothesis testing, we might start to think, what is the probability that something happens just due to chance? And using this type of framing of saying a 95% confidence interval that a value falls within compared to falling out, we could say, what's the probability that it's just due to random chance that we didn't get the estimate right? So this is just building up towards that, and just framing it in this way will be consistent going forward when we get into hypothesis testing as well.
Question, with the equations on the bottom, that's the mean minus 1.96 times the standard deviation divided by the population, the square root of the population, right?
Not the population, but the number of
The
observations
number of,
we're looking at.
got it. So the 0.025, is that the standard deviation, or that's just the percentage of the likability?
Yeah, that's a great question. And I just want us to think about drawing the area under the curve.
Mm-hmm.
And if you took out 95% of that from the middle, which is that's our confidence interval, then you have that 5% on both tails. And so that 0.025 is just 0.05
Half of the 5%.
divided by 2.
Got it. Okay.
And so that's what we use to get the Z score.
Okay. So that is, that's the Z score right there.
Was
Or part of it.
1.96.
Yeah.
And that represents that number of standard deviations away from the mean that would provide just 0.025% of the area under the curve to the right of it.
Okay. All right, cool. I just didn't want to go without figuring that part out.
No, that's really critical, especially most times when we talk about confidence intervals, it's usually going to be, 90, 95, 99, because that is kind of just more useful than saying, 50% confidence interval. So you might
so what you're really confident about was 50%, right?
Yeah, it's kind of like, oh, just could be random chance at that point, a flip of a coin. So yeah, so
the X with the little line above it, what does that mean again? I forgot.
That's whenever I say X bar, the bar
X, okay,
is what's on top of the X, and that's the sample mean.
Okay.
And we use this syntax mostly just to say that this is not the population mean.
All right, cool. Just making sure. Thank you.
I have a quick question.
Sure.
What's the difference between the sample mean and the population mean?
Yeah, exactly. That's definitely just part of when we're using statistics. We don't really know the population mean ever in kind of a true sense of, unless similar when we talked last class of taking the census of the United States population. That would be a population mean because we went out and asked every single person to submit a data point. But again, there's kind of bias in that. And is it truly representative of every single individual? That's what I mean when we say we don't really ever know the true population mean, but that would represent our statistic for the population parameter compared to the sample mean of just taking a random sample of, let's say, 100,000 United States residents, and that would be our sample mean. That would represent the population mean without actually going out and asking every single person.
Okay, but it's not that accurate still, because 100,000 people could still be the same types of people.
Yeah, I mean, exactly. That's why in the last class talking about how we take a representative sample, because the goal would be to have a large enough sample and take enough estimates over time where we could have that distribution of samples that would get a representation of the population.
Okay.
And that's also why using confidence intervals is appropriate, because we can say based off of these samples, we have this confidence interval that it's between these distributions. And that's why saying this 95% confidence interval accounts for that area under the curve. Thinking back to like the Plinko, if we dropped a ball 100 times, 95% of the times we drop the ball would be within, let's say 5 to 8. If you were to number all those pegs, like 0 to 10, most of the time it'll fall within these intervals, but sometimes just due to random chance, it'll fall outside. So we're trying to gather all of those sample observations to create an understanding of what is the true population mean using distributions and probability when we see a ball fall. Did that help to clarify?
Yes.
Excellent. Excellent questions. I'm really glad you guys are here to ask these questions. So thank you. So let's just walk through a sample We're going to use this Doritos bag just for consistency from last class, because a lot of these concepts we're discussing really build on each other and are all pretty related in lots of ways. So going on, this sample of 25 Doritos bags had a mean weight of 1.02 ounces per bag. Let's construct a 95% confidence interval for the mean weight of all Doritos bags. So let's assume that the weight is normally distributed with a population standard deviation of 0.03 ounces. And just talking through what we just said, when we say these estimates and population parameters, again, it's really still estimates of the true value itself. So just a caveat, when we talk about these things, a lot of the times it's just based off of an estimate, but we're using these values to now construct confidence intervals from. So just want to highlight that when we are using these things, that it is good to look further beyond, we state these input values and we're using them to construct our understanding of how things work. So just wanted to caveat that. So we can now plug these values into the following equation, which we just looked at in the last slide, to construct this 95% confidence interval. So because we're using that same area under the curve, we can use that same z-score value, which would associate with that 0.025 area under the curve in both tails. So we can use this 1.96 anytime we're doing a 95% confidence interval. And now we use that standard deviation and our sample size of how many observations we're taking in this sample, which was 25. And we can now say plus or minus 0.012 ounces plus the mean and minus the mean. So we can say the mean weight of all bags of Doritos falls between 1.008 and 1.032 ounces. And while it's common to report the 95% confidence interval, we can also use any level of confidence, ranging from 0 to 100 using our area under the curve. So next, I'm just going to walk through how we would go about this for other confidence coefficients. And we use this value of A, or alpha, or Greek letter alpha, to equal the allowed probability of error. Later, when we get into hypothesis testing, this will be used as our significance level, but more on that in the next class. But just wanted to highlight these terms and how they're all related. And this value of alpha is defined by the probability that the estimation will generate an interval that does not contain mu. We'll use this confidence coefficient to represent this probability that the estimate will generate an interval that contains mu. So it's just the two sides of the coin of what's the confidence that we did not get it right. We can also use that to say, what's our confidence that we do get it right? And that's why we would subtract that from 1 to get this probability of error. If our confidence coefficient is 0.95, we can use this probability of error to actually calculate that margin of error and be able to account for the probability that the estimate will not generate an interval that contains mu. So the way we do this, just to walk through it, let's say our confidence coefficient of 0.95. So we might see A equals 0.95. We can now say the probability of error, where alpha actually should really, in this case, be, sorry, I think I mixed up my phrases a bit. So let me just walk that back and clarify. Because if we are saying calculated confidence interval of 0.95, the confidence coefficient is 0.95, but this probability of error, alpha, is the opposite side of that coin of when we don't have the estimate be within the interval. So that's the opposite. That's what we're actually using for our error margin. Does that all make sense? I got that a little mixed up, but the confidence level is more so when we get it right, and this probability of error is when we get it wrong.
I'm not gonna lie to you, I was a little confused just now.
Yeah, me too.
Okay, no worries. Let's use, just looking at this, area under the curve, we're saying the confidence interval is that area in the middle of that 95% of this area under the curve. And this value of alpha, or this like error that we're calculating for, is just the opposite outside of that area of the tails. So it's just the way we assign values and talk through these things, like the terms we use to say the confidence coefficient is everything in the middle, and that value of alpha is what's in the tails.
Now I get it.
Okay, awesome. Yeah, it wasn't anything necessarily new. It's just applying the right terminology.
So if it was 100% confidence level, there would be no A, or alpha, I should say.
Right. If you are 100% confident, yes.
And since there is a 95% confidence, the A equals 5%.
Yes.
Okay.
Exactly. And we'll walk through what that looks like for 0.99, but we can take the same exact approach, like, because I always think it's helpful, just let's use a formula that's generalizable, where we would subtract that confidence coefficient. So if we were doing this for 99%, we would subtract 0.99 from 1 and just divide that by 2 to account for both tails. But I'm jumping ahead a little bit, but that's where we're going essentially.
I have a quick question. Why is it to the left of the 95, it's negative, and to the right, it's positive with the tails?
Yeah, if I understand the question correctly, that is because we have, think of this graph where the x-axis would represent, the Doritos bag of chips weight, where we want to say the mean estimate is right in the middle, but we have this variability of where the mean of the population would be, where we could get it below that interval or above that interval. And so that's why we subtract that margin of error from the left and from the right, so that we can say plus or minus to account for that standard deviation in weight. Does that answer your question? Maybe I misunderstood.
Yeah, no, it does. I think I'm thinking now of the X and Y axis together and the cross, and yeah, to the left, going on the X axis, going to the left are all negative numbers, and to the right are all positive numbers. That's what you're saying? And then right in the middle would be the X bar, or the 95%, I guess.
What do you mean by in the middle?
Like the center of the I guess the perpendicular lines for
So
X and Y.
Sorry, I didn't mean to interrupt.
Yeah, I'm just thinking of like literally like a graph of the X and Y axis.
What is the graph representing?
No, I'm saying like, I'm thinking like on the X axis, I guess the middle would be like 0. And then to the left are all negative numbers, and to the right are all positive numbers. Is that what you're meaning?
I see what you're saying.
Yeah.
And so by 0, and this is jumping back to 2 chapters when we first introduced the normal distribution, where we had, if you were to calculate like the area to the right or to the left of the mean is the middle, and everything is relative to the average. So that's why everything to the left is negative, because we're saying this is below the mean, and everything to the right is positive because this is above the mean.
Oh, okay. Okay.
So it's not necessarily like negative values. It's more so standard deviations away from the mean that are below the mean.
Okay, got it. Okay, thank you.
And just to emphasize that a little further for, other students who might be watching later, thinking about this value of the mean of being 1.02, and we use the standard deviations that would account for the area under the curve, 95%, or 1.96 above that mean and below that mean, is how we then get these values to say the mean bag of chips weight will be 1.02 plus or minus 0.0012, to say the mean weight could be between 1.008 and 1.32 ounces. So we're not getting like negative. It's more so we take the standard deviation and subtract and add it from the mean. And these are excellent questions. So thank you for bringing these up. So I think just talking through it a little bit more is always very helpful. So this is the formula just in all its glory when we're talking about confidence intervals. And this notation where we have that value of Z and we take that alpha or that margin of error, divide that by 2 to account for both upper and lower tails. And this is showing that if Z is the standard normal random variable and alpha is any probability, then Z alpha divided by 2 represents the Z value such that the area under the Z curve to the right of Z alpha divided by 2 is alpha divided by 2. I'm just talking through what we're seeing here, but just thinking about, I think what we just talked through actually does a much better job explaining what it is that we're capturing here. So just thinking how we take that value of the sample estimate and we look at above and below to account for this interval. And just to emphasize it one more time, when we're talking about these assumptions that we make in order to construct confidence intervals, the population must be normally distributed because we're using the symmetry of the tails required just to nicely partition everything. And we also can say the central limit theorem is holding true because we're dealing with the distribution of values over time. And the more samples we take should equate to the true distribution of the population as we start to take a larger sample. So that being said, usually it's considered safe to assume that a sample of over 30 is large enough for the confidence interval to hold true. But later in this chapter, we'll say when we don't have a large sample. So we'll talk through what we use in that case. But for now, let's talk more about this concept of area under the curve and walk through how the formula would be used. So the way we tackle these problems are similar to how we did it in module 6, what we were just talking about in the last questions. With thinking about the area under the curve, we identify that value of A, that is our probability of error. So if we're looking for 95% confidence, then the value of A is 5%. And in order to account for the symmetry of the two tails, we divide this value by 2. And then we use the Z table in the usual way to calculate the probability of a value falling outside of this 95% confidence interval or into the tails of this 5% margin of error. So for the 95% confidence interval, alpha would equal 0.05 and alpha divided by 2 would be 0.25. And therefore we can use the Z statistic of 1.96, which is associated with 0.25 using the table or using Python just to get that exact value. So for the 90% confidence interval, here we'll just talk through what we would use because again, these are kind of consistently used. So you can even start to remember the Z statistic on the back of your hand. So let's talk through 90% confidence interval. We would have 1 minus 0.9, which would equal 0.10. And then we divide that by 2 to accommodate for both tails. And that Z value is 1.645. So for the 99% confidence interval, the alpha would be 0.01. We divide that by 2 to be 0.005. And then we have the Z value of 2.576.
And we got the Z value by referring to the table, I'm assuming?
Yeah, these are from the table.
Okay.
But let's walk through a demo because we can also use Python to get that value. But using the Z table is in the back of the textbook. And I'd recommend rewatching module 6 where we talk through how to use it for that purpose if you wanted to use the table.
Okay. Oh, the Z table is in the back of the textbook?
Yes. Yeah, in the appendix.
Oh, okay. I kept Googling it.
Oh, you can do that, but sometimes it's helpful to use like the same consistent one.
Yeah, I didn't know that was in the textbook. If you have time, could you just show an example of how to use the Z table?
Yeah,
Okay.
we can.
Yeah, because in the last one you had that 1.96, which is, I guess, from the Z table. That's how you got the 0.025 before. I think from the couple of questions ago or examples.
The 0.05 is that area under the curve, and we
Oh,
use
that was
that.
the area, but
Mhm.
you used the Z table before.
Yeah,
Let me just wait.
yeah.
Thank
Let
you.
me grab the textbook version and get that open for us. Here, I'll share my screen again.
I thought you left for a second. I was like, oh my God, what happened?
I'm still here. And so I'll just show you, even just the way I'll navigate it is from the chapter 6, when we were using the normal distribution, just so you can refer back to this, because I believe it also walks through how to use the Z table. So, and it links to it right here to in Appendix B is where we have the Z table. And let me just open that whole thing up. So instead of, yeah, of course you can find this online, but sometimes it's helpful just to use the same consistent one, where this one would be to the area left of the mean being 0. And then we can use the other one to account for the cumulative distribution up to that value of Z. So let's just use this one because it's symmetrical and up into that value. If we wanted to do this on the other side, it's the same exact value. It's just the difference in these tables is how this one is the cumulative density function and the other one accounts just for the tail, which is also cumulative up until the tail. But in this case, we want this Z value on this yellow part. And this is that missing side of the coin. So that's why we'll use this one for now. So the way we would get that value. So let's say we are calculating for that area under the curve being 0.05. Let me just rethink through this. So I kind of almost forget myself because I use, I definitely tend to rely on Python for just getting the value rather than reading this table, but it's important to know how to use this table as well. So let me just go back to where we were in the last section that walks through it, because it's good to reference. Okay, so this is actually looking into the other way. This is good that we're talking through this because this one tells you what the Z value is. So we would be able to match that with the area under the curve. So let's walk through how we would do this the other way, because this one tells you when the Z score is 1.52 to find the corresponding probability. And now we want to go the other way around. Because we have 0.005, for example, for the like 1.96. Let's just walk through where that one is. Okay, it's refreshing my memory too. Because this top one is just the decimal places. And this is, we're going through this the opposite way. So this Z score, this is like negative 3.91. So that's what the top of the table represents. So the Z of negative 1.96, which is what we were finding, we have that negative 1.9, and then we go all the way to the right to the value of 6. And so that is that area under the curve. So that's how we use this the opposite way. Because that 1.96 is kind of just pretty used commonly for the 95. So thinking, I kind of knew you would know where to look for this one since it appears very often. But for that other value, so this one, let me just repeat what I'm saying a little bit more cohesively. So this value of 0.25 for the 95% confidence interval, let's go back to that where we're actually using this. That's where these values match up. So we know the area under the curve that we're looking for is 0.025. And using the Z table, we can look throughout this whole table to find it. Why I said we kind of know it's negative 1.96 is just because this is commonly used. But if we wanted to, and then that's why we would use that value of the Z-score, kind of working backwards to use the table. So let's just look at for the other value that we are talking through that I'm just saying at you. Let's just also look it up just so we can walk through that as well. So when we are talking through, let's walk through this one for the 0.90. So I just said it's 1.643, but if we didn't know that, we would want to use this 0.005. And thinking how that's somewhat similar to where we are, but a little bit closer to the mean. Just thinking intuitively that means it's a little bit less than where we were. I'm saying it like if we needed to find that value of 0.005 instead of 0.025, we will now look closer to the mean and find that value of 0.005. So trying to get close as we can to it.
I think I see it. Is it that 0.0505 next to the, if you go a little down with your arrow to the left, you see it? Would that be it? Because then that has the 1.6.
Yeah, I mean, that's the whole aspect, like kind of limitation of using the table is that it has these predefined things it calculates for you compared to using Python, which I'll show you right now, because that is what I depend on because it's a little bit more exact. But what you're saying is, can we use this value? Because it's just close enough if we wanted to say to be 0.05, and that's 1.64. And I think 1.645 was the 1.6. And I guess so it's right in the middle of these two. It didn't have the exact one. So I think you're correct in looking at this one. And because they don't have exactly 0.05, it's between these two. And that's why they did 1.645 to accommodate for that. So a good eye for sure. Let me show you just again in Python how we would do this, because this was that inverse format. And so let me just grab that, because it's this PPF. It's this one right here. So I will bring that up here because that gets us that exact Z value. So using the stats package and the normal distribution, this PPF stands for, I believe, like the point probability, percent point function. Okay. So if we have this value of A, which would be the opposite of the confidence interval. So I'm just going to write this out where we do 1 minus 0.90 and then divide that by 2 to accommodate for the two tails. This gets us the exact value. So the textbook uses the table, and that's why it was 1.65, but using Python gets us the exact Z value that we need. Did that help? or any other questions we want to talk through.
How did you get the one minus 0.90 again?
Yes. So that is, I'll use the slides to talk through
Oh, I
that.
see it. I see it. Yeah, you did have that formula. Oh, you're subtracting it, the confidence that you want from 100.
Exactly. So that's this
Okay.
slide.
Okay, yeah, I see that now. And then since you're trying to get the Z, which was the A value, that's why you're dividing by 2 to get it symmetrical.
Exactly.
Okay.
And it'll be very similar process for 95, 99, 90. So once you just know the steps and it makes sense kind of why we do these things, of why we're taking the alpha of the tail, is because that's that area under the curve we're trying to account for, to say like, what's the probability that we get this wrong due to, variance in our sample or just due to random chance. So we're trying to calculate the probability that the estimate falls outside of our confidence interval. And that's why we want this area under the curve. And so that's why we take that alpha divided by 2, because it's that symmetry in both sides outside of the interval. Of like this one, we're kind of looking on both sides. Any other question? I'm really glad we talked through that, because I'm sure, it always helps to walk through something like that again. Any other questions before we move forward?
No. I guess I do have a question. How do I know when to use the cumulative distribution function versus the percent, that PPF one that you just did?
Yeah, that is good to talk through. And in this chapter, we're using mostly just that Z value. So we won't necessarily need to use that cumulative area under the curve. We're mostly just trying to get that interval rather than say the total area under the curve, because that's pretty much what the 95% is saying, is like, that is the area under the curve. We're trying to get just the opposite of that. And we just need that Z value of how many standard deviations above and below the mean is it. So that's when we would use this PPF, which is almost like, just give me the Z score, where you would use that cumulative density function to say, give me the area under the curve up into this value. And that's why in the last classes, when we were doing continuous distributions, that's why we were using that most of the time, because we wanted to know what's the probability that the value is below, 90. And therefore we wanted all of the area under the curve up until that value. Where in this case, we're trying to just get a point estimate to say, from this value, give me this interval of values that would fall above and below that point estimate. Does that make sense?
Above and below. Okay. Okay. Yeah, I think that makes sense.
I think if I could create almost like a rule for when to use what.
Yeah, that'd be good.
Yeah. So if we're trying to calculate probability of a value, we would use the cumulative density function. And if we're just trying to say, how does this value relate to the mean, we're using the PPF. Or let me get the actual, the point function. What's the actual word here? The percent point function.
Okay. Okay, sounds good. Thank you. And usually when you use the PPF, you're doing 1 minus whatever you're wanting to be outside of, I guess, right?
In this case, so even in like the last few classes for the continuous distribution, if we wanted to use like that inverse, I don't want to hop around too much by walking through one of those problems, but
Yeah,
if you
no,
remember
you
from
don't
the
have
last
to. Yeah, yeah.
from the last homework where maybe or 2 homeworks ago when we were doing the continuous distributions and it was saying, you know, for miles per gallon, like what value of miles per gallon would it take to be, you know, better than 95% of all cars? We would use this to get that value of like how many standard deviations do you need to be, like what would that value be in order to get above that value. So I would just recommend reviewing the homework solution from the continuous distributions because that homework had both functions that get used.
Okay, okay. Thank you.
No worries. So let's go through this example, just how we would do this in Python from that sample. I think that's where we left off. Yes. So this area under the curve brings us to the demo where this will be very similar to the homework for this chapter, where you'll have example scenarios like this, and you'll need to construct. I believe it really won't ever be anything too weird. When I say weird, as in, you know, like calculate the 85% confidence interval, it's kind of tends to be useful to have these values. So this function just uses that formula we learned, and this will just simply output that estimate of the mean and plus or minus this confidence interval. And in this case, I say, give me that value of Z, but if we wanted to use what we just talked through to get that value of Z, we could make this a more robust function. Because this would only work when you already knew the Z value. So anytime we're using 95, this is always the Z value. So just wanted to caveat that what we're doing here, this just defines the variable inputs from this example, and we can just output that value.
So hopefully it's 95 from now on.
Well, you can't guarantee that. So that's why with that PPF, we can, let me just show you that in case you didn't have that of 95. But I appreciate the optimism. So if we wanted to do this one, you know, of saying 95. So maybe walk me through what we would do to get that Z score if we wanted to use this PPF.
Okay. So we're gonna put the stats. No, not stats. No. We want the Z score.
I'm asking what should we put in for A here that we're trying to calculate for?
So yeah, we probably could put 0.5 or 5%, right? If we want 95% for the Z score.
Yeah, exactly. So how did you get there? Just in case.
So just did 5 or 95 minus 100 and got 5 or 0.5. Or 95% minus 100%. Or the other way around, I'm sorry. Whatever it is.
It doesn't matter too much because we would use like the negative value of that, but just for consistency there. But we're missing one thing, because if we get this, then this value of A.
Damn, what were we missing?
And this actually is just like 1 minus.
Oh.
My bad.
We're still missing something?
Yeah, because this would be the area outside of that 0.95. So back to the slides. So that is just accounting for 0.95 of everything in here.
Oh, we gotta divide it by 2.
Yeah, exactly. Exactly. So now we take this and divide it by 2. And now our value of A accounts for just that area under the tail. And I'm just hopping back to the Z table. So now we're just taking just one of those tails, because before that 0.05 would be for both tails. And now we're dividing that by 2. So we can either use the Z table to get that value, or we can use this function to get the Z score of A, which is more precisely this value, but we round it to 1.96.
Yeah. Okay. Cool. All right.
Awesome. So nice job. So yeah, now we can, if we had, the value, if we wanted to say an 85% confidence interval, now we have the tools to get that Z score for any value we want without needing to use the table. But of course you can use the table as well. And I just want to play around a little bit with this concept and explore what would happen if we change some of these different input parameters. So let's explore this relationship of margin of error and confidence interval if we had a different standard deviation. So in this case, what would happen if we change the standard deviation to be 0.05 ounces rather than 0.03 ounces? So I'm just going to change this input value. And now we can use the same formula we just had there. Or let me just make sure I redefine these here. But we didn't change anything except this standard deviation. So just want to show you like what are the inputs that we're putting here. When I have these values, let me just print them. So still using the same mean, but now we change the standard deviation to 0.05, still have this number of observations and the same Z score that we're going to use. And so now it's gotten a little bit wider. So let's visualize what that looks like. So this would have that original where the standard deviation, or let me before we get into this, let me just talk through what the heck we visualized. This should be pretty similar to what we were showing last time when we had continuous distributions, where we take each value along the x-axis. And this just accounts for the range of values. So I just said, give me all the values for, or 100 that go from the mean minus 3 standard deviations above and below. So this was that original. That's why I used 0.03 rather than 0.05. And then take a normal distribution from this. And that's why this is the original. And that's why in this case, this is now instead of 0.03, it's our new standard deviation of 0.05. And taking that same formula to now plot that normal distribution. And we can see that the width gets a little wider. So now we're a little less confident in the real sample of the real mean of the population rather than the sample, because our standard deviation is a little bit wider. So now things might vary a little bit more just due to the inherent nature of the variance of the Doritos weight, because the standard deviation is wider. So just wanted to visualize what it is that's going on under the hood. So thinking about that area under the curve, if we think like 0 is that y-axis, just talking through the question that was brought up earlier, for this being the 0 of the mean, that's where we have this vertical axis in the middle. And now we look below and above to say what would be the confidence interval that a sample from this would fall between 95% of the area under the curve. So the larger the population standard deviation, the wider the confidence interval. And hopefully that should make just kind of intuitive sense. The more variance there is in the, the observation data point we're looking at, the more variation there'll be in the samples that we derive from it. And that's how this accommodates for that. Any questions regarding that? Okay, let's talk through what if we change the sample size from 25 to 16. So we take a smaller sample. So now I'll change n to 16 and change back the standard deviation to 0.03. So let me just show you what we're now inputting into our function. And hopefully this also emphasizes just the beauty of making functions is I don't need to redefine things or recreate a formula. Once I have my toolkit defined once, I can now reuse it for new values. So now we have the same estimate of the mean. We have the original standard deviation. And the only thing that's changed now is that the number of observations we're taking, or the value of n, is now 16 rather than 25. So using that, now we can start to compare. And just looking at the numbers, it's kind of, I think for me, it's hard to say like what actually happened here. But if we wanted to subtract, these values from the original, that's how we would really be able to see. But let's just visualize it to see what happens as well. Like, did this get wider or narrower? Kind of intuitively, what do you think happened? Or I guess now you see these values. Or judging off this plot, what do we see happening here when we have the original and now when we take a smaller sample size? What do you see happening?
Did the confidence increase? Confidence interval?
Yeah, I mean, in a sense, I would say it's more that the area under the curve is getting wider. So that if you wanted to take that confidence interval, yeah, you needed to widen it a bit more because the sample size is smaller. There's more chance that this distribution is kind of more due to chance. And that's where in the formula that we have, that's why we take the square root of the number of samples, is because we're dividing by that uncertainty due to like a smaller sample size. And so that makes the distribution wider, and therefore the confidence interval increased, as you mentioned, because we're now accommodating for the wider amount of variance that would occur due to a smaller sample size. So it's not saying like we're more confident, it's more just the interval for where we say this value can fall between. Maybe just getting back to even like that shipment of your Amazon package, we're pretty much actually getting like less certain of your package being between 2 to 3 days. And now we're saying it could be between, 1 to 5 days, because out of the samples we took, it's actually smaller. So we can't be as certain that your package will be delivered between 3 to 5. So now we kind of have this wider confidence interval where we're less certain.
So we're saying that whenever we decrease the sample size, there's less certainty because
Exactly.
There's not too many variables to, I guess, judge accurately.
Exactly.
Okay.
Yes.
Okay. I get it. So it's basically like when it comes to surveying people, like if you survey 100 people, you get like a certain amount of answers and you can kind of guess it. But if you survey 1,000 people, you're more likely to get the consensus right?
Essentially. And that's why we use this interval to accommodate for that lack of really knowing anything. So we can be more certain that the value will fall between these intervals if you were to test this, like 100 times against like the true population mean. So you could say like with a wider population, we can be more certain that we will get it right more often compared to if you took a smaller sample mean, smaller sample size. You're less certain that you actually got the whole population right. So I was just kind of repeating what you said, because yes, exactly. So let's just talk through one other experiment of what if we change the confidence to, we want to be even more certain that we are right. So even if, I've never seen anyone say I'm 100% confident that this is exactly what will happen, because that's a pretty bold statement to make in science, because you're likely to not be 100% right all the time, just due to randomness and chance and kind of just the variance in how things work in life. So
The weather, I was just thinking the Weather Channel, sometimes they'll be like, it's 100% chance of rain,
Yeah, I think that the textbook uses the weather as an example to talk through, because exactly. And thinking through that example again, they could say there's a 70% chance of rain. That also means there's a 30% chance that it won't rain. So they're kind of accounting for how they might get it wrong by saying it in terms of confidence intervals, so that you can't tell them that they got it wrong. So yeah, when they say it's 100% chance, they could generally get it right most of the time, but that's why they would state that confidence interval in the news. So I would definitely encourage you thinking like elsewhere in life, like when do you use confidence intervals rather than saying like an exact value? So we use statistics all the time. Any other thoughts before we move forward?
No.
Great. Well, thank you for all those examples too. So let's just talk through if we were to change this from 95 to 99. We would use that same formula to subtract that value from 1 for all the area under the curve. And now we're just taking that 1% that's not accounted for by that 99% of values, and we divide that by 2. And here is where I use that Z value to get what the Z score would be for this. So now our value of alpha is 0.005, and the Z score that accommodates for that is 2.57. And so now I'm just changing the number of observations back. Let me show you what we're putting into this. So now everything is back to the original, but instead of the Z score being for 95, which was 1.96, now it's for 0.99. Now, Darren, if you did want to just memorize these Z score values, if you wanted to memorize for like 0.9, 0.95, and 0.99, that might be good because that's pretty consistent. But it's also good just that we talk through how you would calculate this in case you wanted to get crafty and say, 96%.
I'd rather just calculate it.
Yeah, exactly. So
too many numbers.
Yeah, a little bit. I agree. Mostly just to bring up, it's kind of tends to be consistent in the homework questions and kind of in life when we use these confidence intervals and when we get into hypothesis testing as well. And these will be like the significance values. If you ever see like a p-score of like 0.05% significance value, this is the exact same concept, just applied to a different scenario. But don't worry if you've never heard of those things, because we will definitely dive into that in this class. So anyway, when we have this confidence interval that that we want to be more confident, now our values are between these for the bag of chips. So let's just compare this, because I forget exactly the original one that we had here. So I'm just going to copy and paste this. To just show how this changed. So if we wanted to, subtract this interval from here, just so we can have like the concrete evidence, but our ranges now are more wide because we want to be more certain. Let me make sure I got that right. it's the same on both sides, which makes sense because we're using all the symmetry here. So instead of it being between 0.004, well, let me even just use this top one. So now we have this 0.015. I think that's actually a lot easier to interpret than what I was trying to do. We went from 0.012 to now 0.015. So we have this range getting wider because we need to be more certain. So we want to, or more certain that we're correct. So we give a wider interval. And that brings us back to, like, why is any of this important? Why do confidence intervals matter? I like this quote that actually Warren Buffett once referenced from the economist John Maynard Keynes, where he said, "I would rather be vaguely right than precisely wrong," in describing how he determines the appropriate cash flow measure of a company. So stating that determining the value of a business is not a precise exercise, but it's neither random guesswork. So that's really what we're doing here, is trying to be getting precise as possible, but not just stating what the value is without really giving this understanding of the uncertainty that exists. So this approach exemplifies this scientific theory as it relates to using confidence intervals. So specifically how we use statistics to quantify our uncertainty and use it to inform the estimate. And building off that, we can start to use this scientific theory to measure our models of the world. And we need to consider this uncertainty of any prediction we make. So I'm just going to introduce these concepts of accuracy and precision, just to bring this back to the real world and why these things are used. And this should also be a bit of a refresh from chapter 1, when we discussed how the weights of elephants could change depending on the sample taken or any discrepancies in the scale we're using. And we show this target chart of all the ways we could get the measurement wrong, where our estimate could vary all over the place. Or we could, that would have low accuracy, and we're looking at precise of how often would we reach the bullseye of the true value. So we should think of confidence intervals as this measure of how likely we are to make an accurate prediction of the population mean using our sample mean. So thinking of like this area under the curve of like, how often do we really get it right? And how often do we get it wrong? And what's the proportion of those instances over a distribution? And I'm bringing this up of hypothesis testing because this is where we're going. And I want to connect these concepts before we even get there, just to think of how we can use this confidence interval outcome to test the probability that the estimation procedure will generate an interval that contains mu. And this brings us to some more sophisticated methods of measuring our accuracy. And I'll talk about type 1 error and type 2 error, and we'll talk about this again in later chapters. But this is relevant here because a type 1 error means that we predicted something to happen and it didn't, or a false positive, where a type 2 is the opposite, where we predicted something was not going to happen and it actually did happen. So thinking if this was, like a medical test that you're getting tested for something and they say you do have the illness when you don't, that would be a false positive. And what's perhaps more dangerous is if they say you don't have this illness and you actually did, which would be the false negative. So kind of depending on whatever you're modeling in the world, you might be thinking like, what's more important, that we get it right more often, or do we not get it wrong more often? Kind of thinking of the use case in the sense of of an illness test. It's probably better to over say that you're sick because you might get, a follow-up test compared to missing that you were sick and then you go out and perhaps spread whatever virus you might have. So just talking through these aspects, because this will come back to hypothesis testing, but also it's relevant right now when we say, what's the probability that our sample estimate falls within the range of the true, population mean? But more on this later. Next, actually, I want to talk about beer. and specifically the statistician, chemist, and brewer who served as the head brewer of Guinness in the early 1900s. So I want to talk about William Seeley Gossett, who developed this new statistical methods both in brewery and on the farm that are actually now very central to the design of experiments, significance testing on repeated trials, and to the analysis that he did, which tested different barley varieties and different lab results and use of fertilizers to essentially get the best beer possible. So Gossett worked in the biometrics laboratory of Carl Pearson. So some of these names should start to get more familiar as we go through this class, because a lot of these different scientists had similar theories that they were all testing. Where Pearson, we talked about this with the correlation coefficient. So he actually studied, Gossett studied under Pearson, and Gossett went by the name of Student to protect the trade secrets of Guinness, and was only allowed to publish his research on the condition that he does not mention beer, he does not mention Guinness, and he does not mention his own last name. So he uses this moniker of Student. Some say that this might be because of a notebook that he had called the Student Science Notebook. And Gossett's most notable achievement was called the Student's T distribution rather than Gossett's T distribution. That's what we're getting into next, is this T distribution. So this is just introducing Gossett and his work and kind of where this came from and why. So this paper here that I show a screenshot of was published in Pearson's journal Biometrica under the pseudonym of Student, and the title is Measuring the Probable Error of a Mean. And this paper is all about measuring the likelihood that a sample mean approximates the mean of the population from which it was drawn. So the probable error of the mean, like its standard error, is a specific estimate of the dispersion of its sampling distribution. And as we've been talking, this dispersion is this foundational step of statistical inference. So in short, Gossett's task as apprentice brewer and later master brewer was not only to assess the quality of the natural products, which with their inherent variability, common to all agricultural products, whose quality is dependent not only upon the crop itself, but also on climate, soil conditions, and also to measure all these things in a very cost-effective manner. So this necessitated using experiments with small samples to draw conclusions that would be applied to the large-scale brewing process. So in order to brew this very high-quality Guinness beer with cost-effective experiments to make sure that the crops and the agricultural processes we're using resulting in a significantly better, quality brew. So we're going to apply these concepts and how he did that experiment. So one thing to mention, he was not able to use these conventional statistical methods that we just learned in this class based upon the normal distribution to draw his conclusions, because this sample size is very small. It's under 30 in this case. So he was taking smaller samples where we don't know the standard deviation of the population. So, and that leads us to this T distribution, because the crux of Gossett's work in this paper conducted experiments on small samples of various barley crops, soil conditions, and climates that could then be applied to the large scale brewing process. And this T distribution was discovered because using small samples, the distribution of the means deviated from the normal distribution. And at the same time, statistics relied on what is called the large sample theory, which requires large samples of 150 or more to really work. So in order to accurately compare the means of a quality metric from a small sample, perhaps as the hops quality between a sample of barley crops with two different soil conditions, a new distribution was needed to calculate the probability. So this is a chart from his paper that compared the confidence limits and looks at the standard deviation between two populations. which could then be used to test whether there is evidence of a difference between the two averages based on the sample size. So this is the number of measurements taken from a particular hop crop, for example. If there was no difference or zero difference between the samples, let's just say, there's some metric of quality in this hops. So if one sample of hops was planted with a specific soil condition compared to the other, and he's trying to test, hey, is there any statistical difference between these two crops based on this variable of soil condition, for example. So if there was no difference, we would expect the means to be the same. But if there was a significant difference in this quality of hops that's derived, we would expect to see the distributions of that quality be statistically significant enough different from each other. So that's where we're using these confidence intervals to assign this probability that there's this difference, and kind of using that area under the curve. If you see this like X right in the middle of perhaps there's just this random chance in the sample estimate that resulted in these two distributions really not having much difference at all. So this is the problem of the t-distribution, and the t-test solves it. And these statistics are used in essentially every field of scientific research, such as biology, psychology, biometrics, economics, and medicine. And it's all started with this goal to brew great beer in Guinness. So let's discuss how to calculate the t-distribution and when we would use it for our homework, but also applied in real life scenarios. And in this chapter, I linked to a little bit more on Gossett, because I think just the backstory is kind of interesting, and how it was used and why and when is kind of fun, I think. So, okay, so how to calculate. Really, the difference here is previously we have this population mean that we're suggesting when the population standard deviation is known. Again, like as we were talking, in reality, it's never really known. But there are these instances when the population standard deviation is somewhat predictable or stable, and therefore can be estimated from prior experience. So everything up until this t-distribution, we would assume that there's stability in the population standard deviation, and we kind of just use this estimate of it to calculate these things. But for the t-distribution, because our samples are small, we can't necessarily claim that our estimate is the same level of like credibility in a sense. So that's why we still are going to use this estimate, but we just label it S rather than the standard deviation symbol when we use this t-distribution to capture the confidence interval when the standard deviation of the population is unknown in a sense. So that is the difference here, where we, instead of using the Z table, we'll actually use a T table, and that follows students' T distribution. And when I say this T distribution, it's actually a family of distributions similar to the normal curve because it's bell-shaped and it's symmetric around 0, where 0 is the mean. But a key difference in the shape is that there are these broader tails than the Z distribution, and that accounts for this very small sample size. So in this graph here, you see this label of DF, which stands for degrees of freedom, but we'll get into that a little bit more. But essentially, that's like the sample size. So when we have smaller samples, the tails get wider, similar to what we talked through in the last demo just now of when we were testing out these different things. So this is a new item to introduce, this degrees of freedom, which sometimes in nomenclature is just labeled DF. And this degree of freedom accounts for the extent of the broadness in the tails of the distribution. And this specifically accounts for the small sample size and the variance inherent to that whole process. And the way this is calculated of degrees of freedom is just taking the number of observations, or N, and subtracting 1 from it. And I'll soon just get into why we do that. But that, if you just wanted to know, like, how do I calculate it? You just take n minus 1, and that's the degrees of freedom. And the t distribution is defined by the degrees of freedom used. And this formula here, it should be very similar to the last one when we're using this z-score that accommodates for the number of observations there. But when we have this degrees of freedom, this means that the number of independent pieces of information that go into the calculation of a given statistic can be freely chosen or free to vary. So next, I'm going to talk about this concept so it makes more intuitive sense of what this degree of freedom actually means. So let's forget about statistics for a moment. Imagine you're a fun-loving person who loves to wear hats, and you couldn't care less what a degree of freedom is or what that meant, because you believe variety is the spice of life. But unfortunately, you have constraints in your fun-loving life, and you only have 7 hats. And yet, because you love hats so much, you want to wear a different hat every day of the week. So think this through. On the first day, you can choose any of the 7 hats to wear. On the second day, you can only choose from 6 of the remaining hats because you already wore 1. And on day 3, you can only choose from 5 hats, and so on. But by the time day 6 rolls around and you only have 7 hats, you really don't have a choice between the 2 hats that you haven't worn yet. Or not 2 hats, like you don't have a choice. It's that last hat on day 7 that you must wear that remaining hat. So you have 7 total values, and you only have 6 degrees of hat freedom in which the hat you could wear varies. So this degree of freedom just accounts for this constraint in a calculation for a piece of information that can be freely chosen. So when you're left with just 1 hat, there is no choice. So it's essentially a given. So that's what degrees of freedom is accounting for, of like how many numbers in this permutation can we actually calculate. So if we only had 7 and we're trying to say on each day you take away 1 hat, you're left with just 1 hat at the end, and you don't have any degrees of freedom. It's just that 1 hat. So we use degrees of freedom to account for this lack of needing to calculate that last value because it's just a given. And this concept of degrees of freedom will appear again as we work with hypothesis tests, because it indicates the number of independent values that can vary in analysis just without breaking our constraints. So for the t distribution, the degrees of freedom affect the shape of the graph. And as the degrees of freedom get larger, the area in the tails of the distribution gets smaller. And as the degrees of freedom approach infinity, so let's say you had infinite hats, then we really don't need to think about this degree of freedom constraint anymore. And the t distribution essentially just becomes the normal distribution, where the tails start to just be more narrow and aligned with the normal distribution. So to summarize, the degree of freedom bring back the sample size to account for the chance outcome of a significant difference in the sample means due just to the variance and randomness in the samples taken. Any questions on that? Okay. So next, let's walk through a quick example for how to use the t-table for calculating the probabilities from a t distribution. Here is a screenshot of the t-table, which is also in the back of the textbook, that has a more complete table. And the biggest difference for using this compared to the z-table, which we also reviewed in this class, which was helpful now to compare, is that we have this degree of freedom parameter here. And this table is not as comprehensive as well, because it only lists corresponding values in a more limited constraint because of these degrees of freedom. And another difference is that rather than a cumulative probability distribution, the t-table just provides the probabilities in the upper tail of the distribution. So similar to what we talked through in the beginning of class, it only looks for the area under the tail in this case, because that's really what the t-table is used for most often. And so in order to calculate, we need 2 pieces of information. the alpha value of like what is the estimate error that we're trying to calculate for, and the degrees of freedom. And we use the rows and the columns to obtain the exact area under the curve. For example, to compute the t-statistic for alpha equals 0.025, we would navigate to the column of 0.25 and then go to the exact row that would provide us the degrees of freedom listed. And if the t-table does not have that exact value, you can use that average between, or we can also use Python again to calculate the exact probability. And to calculate the confidence interval, we use the same exact formula as before, just now we replace the z statistic with the t statistic and use the sample standard deviation taken. So let's walk through another example, and this is essentially the towards the end of class for what we'll be covering today. And I'll walk through in Python how you would go through this and go through a couple more examples just to really hone in these points now. So let's just take an example where we're looking at different cars. So this is just a broad overview before I dive into the example in Python. I just want to talk through the input parameters that we'll be working with, where we'll look at a population of car mileage records and try to take an estimate, the mean of all cars with 90% confidence interval. So that's just the question as if this was homework. And we take a sample from a data frame of 25 cars, and we'll test if this sample mean is within the 90% confidence interval. And we calculate the sample standard deviation and the degrees of freedom. And degrees of freedom, we use our formula to say it's the number of observations in our sample minus 1 to account for these degrees of freedom that we actually can calculate. So in this case, our alpha value is 0.1 because we're taking just the area in one side in that case, and then we divide that by 2 to get for both. So our alpha value is 0.05 is what we'll use when we're using that t-table. And we have that t value that we just calculated from the t-table, but I'll also show you in Python how we have that function as well. So first we'll run through an example from the textbook, and then we'll take a bit of a detour to explore this further.
Can you just show us the 1.711 on the t-table again, please?
Yes. So in this case, we have the 0.05 for alpha. So if we were to do that here, that's this. If you see my my mouse, that would be this column. And because our degrees of freedom is 24, we just go all the way down here to this row. And so it's why it's 1.711.
Oh, so the one tail is the A, right?
This,
I just see one tail, or you're looking at the 0.95 and the 0.9. Is that what you're looking at?
so this example that we have here, this I was just like telling you, alpha equals 0.025, and we can use that to calculate the degrees of freedom. But in this case, now we're bringing it back to the 90% confidence. So now we need to take that alpha and calculate it to get that area under the curve. So you're right to say that this table aligns with just one area. And that's why we divide that by 2 to get the value when we have a confidence interval. So if the textbook, because there is a question in the homework that just gives you this value of alpha and tells you degrees of freedom, you can simply just plug and play that with the table and just, follow this for 0.025, you would go here. And so for 2 degrees of freedom, the answer would be 4.3. For 5, you would go down. And for 50, you would go, all the way here and just take the average between 40 and 60. But when we're talking through here, where we have this confidence interval, we need to define that value of alpha. So that's why we use the same format we used before, where we minus 0.9 from 1 and divide that by 2, because we want the area in both sides of the area under the curve. So that's why in this case, A equals 0.05 when we wanted to calculate that, because we're using the same chart, but now we're just diminishing it to be like the true area under the curve that we're calculating for.
Okay, I was just wondering when, because I see it says one tail on the left. I'm just wondering when we would use the one tail or the two tails.
Oh, I see what you're saying. Yeah, and again, it's kind of however you want to slice and dice it. We're all talking about the same thing. And that's why it lists it there like that. That's a good question. Because yeah, that's exactly when we have alpha, equals 0.1, we make that into a one tail by dividing that by 2. But if we wanted to not do that step, this table makes it a little easier for us. And it says, hey, these are the same exact things. So it's just
Okay,
saying,
thank you.
yeah, that we're using it in two tails in our confidence interval case, but that it also just this table is actually just giving you the one tail. As long as, you're dividing the two tails in half to accommodate for the one tail. It's essentially saying the same thing.
Okay, got it. Thank you.
Yeah, no worries. Okay, so now the rest of this class will just be working in Python to walk through using the t-distribution. So this is an example from the textbook, and this will be pretty similar to the homework. So just for, before we get into that car example, these were just some other things. So what that slide was setting up, we'll get into a little bit, but just before we get to that, this is an example where we have 80 hockey pucks, and we want to construct a 90% confidence interval for the population mean weight, assuming that this population standard deviation, let me just make sure that this is, actually, sorry, this was from, we probably should have, I'm hopping around a little bit. This was from the last portion because this uses just the z-score. And it just goes through another example. So you can go through this yourself. I don't want to talk through this because we pretty much talked through all these different points. And this just goes through the example as well. So I think I just added that there because this is really what I wanted to get to, because now we're talking, okay, back to where the sample, this makes more sense of where I was going when I made this presentation, where we're talking through this mean of car miles per gallon. So this is from the textbook. So we read this in here from using pandas to read the sheet name that we want. And let's just see, it has 25 rows, textbook. And this is the data we're working with. So this is just miles per gallon. And for the number of observations, it told us 25, but we can also use the shape of the data frame to define the value of n. Just to show when we use the shape to say we're just taking this first value in this tuple to say, give me the number of rows, because this one says the number of columns. So for calculating the 90% confidence interval, we use that same exact thing that we've been talking through to divide that by 2 to get alpha. But now if you wanted to use the table, you necessarily could just use the 0.10 instead of doing this, but it would be equivalent. When we're using the degrees of freedom, we take the number of observations and -1. And so this is similar to when we had the normal distribution, which we went through in the beginning, but instead of the norm, it's now using the t distribution. So it's the same exact syntax when we have this percent point function. Except the only new thing is now we have this degrees of freedom. So this is instead of using the t-table, if you wanted to use Python to calculate the exact t statistic. And that
quick question.
Yeah, sure.
If we replace the T with the Z, would the answer be completely different?
So you're saying do Z there?
Yeah, would it be the same answer if we had a Z score instead of a T score?
Okay, I see your question. So, and just the syntax. So are you suggesting what if we looked at the normal distribution compared to the T distribution?
Yes.
How would these be different? So the normal distribution doesn't care about degrees of freedom. So we wouldn't necessarily need to have this there. But let's see how it would be different. So it's different, but only slightly. And so that's a really good question to think about, because this T statistic is a similar distribution, but because it has the degrees of freedom, it has these wider tails. And therefore it makes sense that the number of standard deviations away from the mean would be a little wider, even if we use the same value of alpha. So we can think about these in the exact same way. It's just accounting for the distribution having wider tails.
Okay, I'm just making sure. So just gotta make sure we have the T where it's supposed to be. Got it.
Yeah, and in the homework, it is very discrete with now, in this section, use the T statistic. But kind of in real life, you would apply this when we have, degrees of freedom, you have a small sample size. And therefore, you can't really be sure that this standard deviation estimate is as stable as it would be when you had a wider sample. But for the purposes of our class, it'll usually just be told when to use the T distribution. But yes, so definitely make sure when you're answering the homework, if you're not using the tables to calculate the Z statistic and T statistic, that you make sure whatever you're answering has this very different value, because it's important to know the difference and have it be accounted for.
So
Because if we did, yep.
Oh, sorry.
No,
So
go.
whenever we're doing the T distribution, we're doing stats.t.ppf.
Yes, exactly. And if we're using the normal distribution, we just use dot norm instead of the dot T.
Okay, and the DF at the end, what is that's degrees of freedom, but aren't we calculating that? Or where it's known?
Right. That's just part of the information we need to tell the T distribution. And that's known because we have the number of observations of 25 in this sample of cars with miles per gallon. And therefore, the degrees of freedom is just number of observations minus 1. So that's just like an input.
Okay. And what is this? So the T distribution is 1.710. What is that telling us?
Yeah, excellent question. So that's the exact same thing as when we use the Z distribution to say this value is, 1.71 standard deviations above or below the mean. So this could be interpreted in the same way. So in this case, for this 90% confidence interval, we're trying to account for all the values that fall above or below 1.71 standard deviations from the mean.
Okay.
So we approach it and calculate things in the exact, not the exact, I shouldn't say that, but in a very similar way. And we can interpret it in a similar way. The T distribution was novel because it accounted for the small sample size due to the experiments of looking at barley crops and whatnot. So you can't really use the normal distribution when you have this small sample. And that's the key difference. So that's why degrees of freedom come in, and we use a T distribution instead of the normal distribution.
So small sample size meaning less than 30, I think I saw, or that was something else, because I saw 30 in there somewhere in your slide.
Yeah, that's usually kind of just accepted as under 30. You would use something like the T statistic.
Okay.
So that's kind of just like but the end of this textbook actually talks about like what is an appropriate sample size to be accurate enough. And I'd say, if we're applying this in real life, we would need to look more into that and test, what is an appropriate sample size. But for the purposes of our class, it'll usually just be use this approach in a sense. But yeah, intuitively, you can think if the number of samples is under 30, that the t-statistic would be used instead of the normal distribution, because we want to account for this very small sample size. Does that make sense?
Yeah, that's good. Thank you.
Awesome. No worries. Great questions. Okay, so let's plot this just to even show what it looks like and just to hone in on this example. So I'm just plotting the histogram of values of miles per gallon. And we see these are pretty efficient cars in this sample. And I have this sample mean where I just plotted a vertical line here for using the mean of this column. And we could see, just to emphasize how you would interpret this value of saying 1.71 standard deviations above and below the mean. So let's just plot this so you can see where that would fall. I'm just going to make this into like t statistic to use it as a variable. So now I can say, let's plot the positive side of this. And this, again, not to occlude what we're talking about by comparing this to what we talked last time when we have these control limits, but it's kind of a similar concept of saying how many standard deviations from the mean is considered out of control or kind of like wrong or something that should be looked into as an outlier. It's all very similar concepts of using how many standard deviations above and below the mean should be considered something that is correct or kind of expected versus unexpected. So I'm just going to call this like upper limit. And then I'll also plot, I'm just going to make this green. And then I'll just do a negative to account for the other side. And just T limit probably isn't accurate. So let me use a better word, like lower deviation from mean. But that's just using this. Well, okay. And the reason why this is all the way over there, I need to subtract this from the mean. So I would need to use this mean and have this one plus. All right, let me think this through. This is not just that value. I'll just see what this looks like. I don't think this is. Because it still won't give us. Well, yeah, this isn't, because I need to multiply this by the mean itself. No, that's not right either. Okay, I might be digging myself a hole for what I'm trying to show, because I want to just show, we'd probably need to use something else to actually visualize what that value would be of above or below. So let me just, to make more progress and finish this out, let me just not visualize that, but maybe I'll do that after and look into what the best way to do that, just for sake of time purposes, because it would look something like this t-stat. We would want to times this by the mean and say how many standard deviations above or below. So I'd want that value, and I would want to times it above and below how many standard deviations. So it would pretty much just look, it should really be a value like here and here on the other side. So, but anyway, I won't go down that alley too much further. So let's just talk through this distribution. It's normally distributed, and therefore, we're just assuming that it's normally distributed, and we can construct the confidence interval using this formula. And this is a function to calculate that. I don't think I need this SciPy because I read in the package at the top. That's coming from here. And so this function will calculate the confidence interval using a column, and it's simply, you just have to tell it what's the confidence you want to use, because it'll use that value to create the T statistic for you. So that would be the input, and it would give you, so these were the values I wanted to plot. So actually we should use our formula for getting those values. So if I wanted to plot those here, this is kind of what I was getting at, because I would want to put these here. So this is what I wanted to do. I just wanted to visualize where that would fall. This would be the lower, and this would be the upper. And these are those confidence lower. Okay, so now we see where those would go to say this 90% confidence interval, that the value would fall here rather than over here to say the true mean of this population. So we're able to see, in this case, this mean is between the interval that we have here. So I'm going to hop on this a little further and just explore if we had a larger population, because here in this case, this little kind of case study, we only had these 25 samples, and we don't really have a population to go off of. This is just this sample. So just for demonstrative purposes, I found another data set from this archive of the Irvine Machine Learning Repository that has a lot of great data sets that can be explored. But in this case, it's just a bigger data set that I'm going to call our population of, let's say, like cars at a dealership, and we'll create a sample from that. So this will be the last thing in class today. So I'm just reading in this data frame from this website, and I had to do a little bit of wrangling to get it in a format that works for us, where I'm just splitting columns and getting exactly what we want. But I'd say don't worry too much about that, because at the end, we're just looking at this miles per gallon. So we have it in the same format. And as I mentioned, we're doing this to assume this population of about 398 cars is our population at this cars in a dealership. And for demonstrative purposes, we'll take a sample of 25 cars and actually test this against the population. So I'm just going to get this population mean. And again, we're oversimplifying by saying this is the population of cars in a dealership. So we have this true population mean, where miles per gallon is 23, which is a lot lower than what in the textbook had a distribution for. So let's just plot what the population of miles per gallon looks like. And I do that using this histogram function to plot it. And I show this value of the population mean right in the middle. So, and we see this is relatively normal. So we can assume normal distribution when we calculate from it, but it's kind of interesting. You have this jump here that I thought, and it is somewhat skewed to the left due to this distribution concentration at around 15. So we're going to use this random sample just to take 25, and this ties in some concepts we covered in the last class, where n equals 25 of, we're just saying, let's take a sample and estimate the mean from that one sample. So I take this data frame column and say, take a sample of 25 where n equals 25, and I give this random state for reproducible results so that anytime I calculate this from the same data frame, I'll get the same sample. So if now this is a new data frame, actually, so it's not really a data, it's a series of values that are 25 from the population. So now I can have the mean and the standard deviation of that sample, because we're just kind of going off the assumption we don't know the population standard deviation, but in this demonstration we do, and we'll use that just to show the difference. So if we plot this distribution, we see that the mean is actually slightly lower than where we had before, where before the sample mean was right below 25, and now our sample mean is a little bit closer to 20 rather than 25. But essentially we see a similar shape, but just with a lower resolution because we have less observations to count from. So a sample of 25 cars yields a mean of 22.1. So let's estimate the mean of all cars in the population with a 95% confidence using this sample. So in this case, I just, instead of, because there might be issues if you read in a data frame as df, that degrees of freedom, you can't use df, the same variable function, because it'll override that. So I just use degree freedom to account for that, and take our alpha value, obtain the t statistic from this. So using degrees of freedom of 24 and our alpha value here in the appropriate way, we have this t statistic that we can now use with our sample mean, and we use our function to get these upper and lower bounds using the t-score. So actually, I don't like what I wrote here because I don't think that this should necessarily be, it's not really this 95% probability, but it's more like, 95 out of 100 times the car would fall within these values. So I'd rather say for a 95%. Okay. And we can use that other function we had rather than this, because this just simplifies it and puts in all the different items we had here. We can use that other function I defined before with this mean confidence interval, and we should have the same values here. So this is just unpacking that function and showing it in a different way. And just to bring this back to how we can now test this as a hypothesis, in a sense, to say this from a sample, is this similar to the population? So let's look at the population mean. And because our value was between 19 and 25, where the true population mean was 23, we can say we got this right because we have the population mean to show like what the true value was. And we just calculated this confidence interval around the sample that we had. And because we have this 95% probability that the mean car miles per gallon will fall between this interval, therefore the interval did contain the mean of the population. So we can say this was a true positive or the correct outcome. And I won't talk through this too much because this is just testing if we were to change the standard deviations and how that would look, similar to how we did it when we just had the z-score. And it'll follow the same type of pattern where when we increase the standard deviation, that the width of the confidence interval ranges would increase, similar with taking a smaller sample. And if we were to use the same function, this one, now we can just plug and play with the different confidence intervals we want to take. So now instead of a 0.95, now we would have a wider confidence interval because of this 0.99. So we want it to be more likely to get it right if we did this 100 times. So we widen the confidence interval. But with this wider interval, kind of the lower the precision is. So back to that package delivery, like you're more likely to get it right to say your package will arrive 1 to 5 business days rather than, 2 to 3. But there's less accuracy there in what you're saying, and not accuracy, but precision. So in the next chapter, we'll start to build upon this t distribution and get into those t-tests, and then get into hypothesis testing, and then other fun things to be continued from there. So thank you very much. I'm going to end the recording.